Cooper pairing. So
Sir,
the problem, yes.
Sir, I have a question from the last class.
So that's the definition of Vk primed K, and what this basically means is that this is a potential Fourier transform the potential. So this scatters two electrons from the state K minus K to K primed minus K. K up minus K down, K primed up minus K prime down. That's the potential. So you get that. So here we just interchange the indices K and K primed, and this K primed square that appears here is just the energy of the free electrons in atomic units. So therefore, or rather the K prime square by 2 is the energy. So this is twice epsilon K prime. So this is what we get as the final state. So what we claim from here is that if we can find a set of solutions, that is a set of G's, such that this energy E here, which is the energy of the two electron problem, that is less than the Fermi energy of the Fermi C that we have, then that would imply that the Fermi C is no longer a good description of the electronic system that we have. So now here, following Cooper's original work, what is often, what we'll assume is that V has a very simple form, this VKK primed. Let me write with the units. And so basically, the two electrons what we are trying to say here is that, so just a minute. So this is greater than epsilon primed, and H cross square is squared twice in this has to So basically what we are trying to say is that both the electron energies are of course higher than the Fermi energy, but their difference is within a certain range, H cross epsilon, H cross omega C, some cutoff of the Fermi energy, and it is 0 otherwise. So this additional two electrons are basically within this range of energy, and this range is H cross omega C. So that's the sort of assumption. Now, therefore, this can be made simpler. So we can just pull out V, and we can write GK as And from that, we get, so suppose now I sum on both sides over K. Now this is just a constant. I'm just summing over K primed, this thing within that range. So that will just can be, and this constant is exactly the same as that constant. So therefore, I can write this as 1 over V is equal to sum of K. Oh, sorry, I have to write a minus V here. This was minus, so this sign will change. Okay, that's the condition you get on V, and or 1 over V. And then what we do is, as we have done so many times before, we will replace this sum over K by an integral, and an integral will go obviously from the Fermi energy here up to an energy range H cross omega C. So if you do that, and since we are integrating this over a small energy range, about the starting from the Fermi energy, that d epsilon, the density of states that appear in the integral, we can just pull out and replace that by the density of states at the Fermi energy of the normal system of the Fermi C that we had. All right, so let me see, how do we get this factor of half? Okay, so if you do the integral, you will get this. This is what you get. Now we will be looking at a situation which turns out to be true for most of these conventional superconductors, is the condition that V times so we'll be looking at this condition. All right, so basically basically what I'm trying to get here is that I'm trying to get an expression for E from this, okay? So you can easily check that this will give you is equal to E to the minus . And then So I'll bring this over here. Now, what did I say? That this is small. So this is a large number, 2 over dV, and exponential minus of that. So we can just, we can ignore that. So ignoring this term here, we get E is equal to if you wish. This was Cooper's result, and this is a very, very important result. Now, the algebra is trivial, but the implications are enormous. So let us try to understand that. Firstly, we got an energy, which is, sorry, this is EF. We got an energy that is less than EF. That's the first thing. So we got an energy which is less than what you would have got putting these additional 2 electrons right at the Fermi surface. But they are above the Fermi surface in energy. But we get an energy of these 2 electrons because of their interactions, which is less than twice the EF. So which already tells you that the Fermi sea is not a good description for the ground state of this system anymore. That's the first point. The second point is that we are talking of a situation where this factor is large. Because this is small, so this factor is large. And there is no expansion of this in powers of V, no matter how small V is. In fact, that whole thing is sort of non-analytic at V equal to 0. So, so for small v, there is no expansion of this in powers of V. So therefore, you would never get this result from a perturbation theory. So this is a non-perturbative result. As soon as you have an attractive interaction between the electrons, the Fermi sea becomes unstable. That's no longer the ground state of the system. So this is a result which sort of paved the way for the formal Bcs theory of superconductivity in the conventional superconductors. Okay, so this aspect you should very clearly understand. What else do we learn from this? One more point. So, write this here. Just a while ago, we wrote this expression for GK. Where this is the free particle energies. So this can be written as. So let us now write all the energies relative to the Fermi energy. So I'll write this as epsilon k minus EF. So this should be written as E minus twice EF. So this we write as so this is a new symbol that we introduce, xi k, which is the free particle energy relative to the Fermi energy, and this is written like this, where E primed is minus. Now remember, these GKs are the weights of the free particle states, whose superposition gives me the two particle wave function. So the weights go as this, which depends on k squared only relative to the Fermi energy here. So in other words, these wave functions, these two particle wave functions obtained because of pairing between two electrons will be spherically symmetric because the weights go as k squared. So because these are spherically symmetric, these are like S wave states, S states, okay? So these two particle states are like S states because they are spherically symmetric. And so the superconductivity that arises because of this sort of pairing are called the S wave superconductors. So the conventional superconductors are S wave superconductors.
Should there be a V in the numerator?
Numerator of what?
GK equal to summation of GK.
Yeah, in the expression of G, there is a V, yes. Yes.
And in the integration that you did, that an actual log thing, so the energy that is required, that is increased because of the two electrons that we add is h cut omega c.
No. H cut omega c is not the increase in energy. H cut omega c is sort of the cutoff energy beyond which this potential would go to zero anyway. So the two electrons are within a range epsilon f to epsilon f plus h cross omega c.
Okay, and the energy is decreasing actually, not increasing.
Yeah, the energy is decreasing. That's the whole point. Okay. Any attractive interaction you have, no matter how small, will lower the energy. Okay, so that's the sort of Cooper analysis, Cooper instability. So this is called Cooper instability because any attractive interaction between two electrons makes the Fermi C unstable. So you have to search for new ground state of the system, and that's what the BCS theory does. Before we get to the BCS theory, a couple of other things that we will briefly discuss. The first thing is that what gives rise to this attractive interaction between electrons? After all, they are all negatively charged. As I mentioned last time, it's the phonons, it's the lattice vibration that give rise to this attractive interaction. Now, in order to fully understand this, and particularly if you really want material specific information as to how strong that interaction is, one has to get into and consider band structure of the particular material one is interested in. Of course, that's a elaborate exercise. We will not get into that. We will not even get into the full sort of general discussion of what the roles of phonons are in screening electron-electron interactions. So that requires more detailed discussion of phonons in metals, which we did not get into. So I'll just mention the outline and argue that it's possible that under certain conditions, you have an attractive interaction. So the bare Coulomb interaction between two electrons is, of course, this. And if you do a Fourier transform of this, you'll get but then particularly in metals, the electrons, any two electrons, do not really experience the bare interaction. There is a screening because there are all the other electrons which are mobile. So therefore, they try to screen the electric field for one on the other, and so a good way of representing that is through a screened Coulomb interaction. Okay. Case is some inverse of screening length, and if you take a Fourier transform of this, this is the Fourier transform. And so this is due to electron screening. Now comes the phonons. Okay. And one can argue that if so screening so this is the sort of effect that you get, where omega is, the frequency corresponding to the energy difference between the two electrons that are interacting. And this is the energy or the frequency of the phonon at that OS vector Q. So that's the effect of the phonon. So therefore, this is actually a function of Q and omega. So the total interaction after electron screening and screening due to phonons is a 4 pi . So as omega is less than this quantity, this term becomes negative. So this sort of gives you a plausibility argument that for some values of omega, since this term is negative, you can be in a situation where this overall thing becomes negative. So there is an effective attractive interaction between the electrons, and the main thing responsible for that is the screening due to the phonons. And a very simple physical picture that's often discussed, you will find in Ashcroft's book also, is that when an electron travels through this lattice of ions, the ions move from their ideal positions because of attraction with the electron. And so when the second electron passes through that region, it experiences a potential due to this moved ions, which eventually leads to an effective attractive interaction between the two electrons, depending on their energy difference. So that's the simple level picture one can draw, but the message one carries from here is that under certain conditions, because of this screening due to the phonons, in other words, electron-phonon coupling, you can have effective attractive interaction between the electrons. And as it turns out, we don't need to worry about so much about the details of this attractive interaction or its origin once we accept that there is an attractive interaction. Many of the essential properties of the superconducting state can be calculated, as we'll see in the Bcs theory. It doesn't worry at all about the details of this attractive interaction. It assumes the same sort of simple, constant negative potential if the electrons happen to be within a certain energy range, and derives all the essential results. Okay, so that was something I wanted to discuss. The other thing I wanted to briefly mention, this relates to phenomenology, not the microscopic theory. It's something I should have done last time, but let me do it now. So we argued that in the superconducting state, the magnetic field is completely expelled from inside the superconductor. So why is that? I mean, of course, it has to be because the energy is lowered. Okay, so we want to see that energy balance, and from that we want to get an idea about the difference in free energies between the superconducting state and the normal state. So the Helmholtz free energy in the normal state so this F is the free energy density in the normal state. And then I have term which arises because of the presence of the magnetic field. And because in the normal state, the field penetrates the entire volume of the superconductor, I have this term where this V is the volume. I mean, one could have avoided this term altogether, but just to be complete. So this V is the volume of the superconductor. And this V external is the volume of the region outside the superconductor. So that's the free energy in the normal state, and in the superconducting state, there is no field inside the superconductor. So this, in this case, I'll only have the external term, where HA is the applied magnetic field. And what I'm calculating is the difference between these two. And so what? Right. Now, what happens at when the applied field is just equal to the critical field? Remember, the critical field by definition is the one at which the field penetrates the superconductor. So right at that field, the energy difference between these two must be equal to the energy due to the external field over the volume of the superconductor. In other words, this just from the definition of HC. So then if you sort of plug this in at HC, what you get is okay. So that's what I just want you to remember, these and this. The difference in energy density, free energy density in the normal state and the superconducting state in terms of the critical field. So finally, we'll get to Bcs theory, and I'll start the discussion today, and we have to have at least another class. I'll have one more class, whatever we can do today, and in the next class, we'll finish it up there. And today I'll continue for another 15 minutes or so, and then I'll take another quiz. So I'll send you a question on magnetism, which you have to work out and send back by the end of the class. So I have a metal in which I have some partially filled band. This is my K space, So in this particular band, or any band for that matter, there are a certain number of K points over the Brillouin zone. Okay, so let us call that number M. And then there are N electrons. Okay. You have to wait for a while before you can see it. Okay. So what we are trying to do is to write down a new, write down the wave function of a mini particle state, the ground state, after we have realized that any attractive interaction between electrons makes the Fermi sea unstable. So it's a new ground state that we are trying to write down, which has such electron pairing built in. So be very clear about it. What we are writing is not a single particle state. What we are writing is a ground state of N electrons forming N by 2 pairs, because there's a pairing interaction. So that's the wave function we are trying to write. And sort of following the wave function we wrote for 2 electrons, in which state with K coupled or paired with a state minus K. And also remember that this pairing was singlet. So if K is up, minus K has to be down. So now we are, so this wave function that we are trying to write is a superposition of such states. And we'll write this in terms of second quantized notation. That's the easiest thing to do. Okay, so let us try to understand this, and then we'll realize that it's almost an intractable problem. Okay, so what are these indices? K1, Ki up to Kl. The Ki is the first and Kl is the last K point. So there would be N by 2 of them, because there are N by 2 pairs that have been selected from this possible M K points that appear in a band. And for each K point, a K up electron pairs with a K down electron. So whenever there is a K up electron, there's a minus K down electron, so on from Ki all the way to Kl. And this state phi naught is the vacuum when there are no electrons. So you are creating these electron pairs, K minus K pairs, starting from the vacuum. There are M total of M K points, and you have to choose N by 2 K points out of that to form these N by 2 pairs. So the possible, so the number of terms in this would be this. And remember, both m and n are, numbers of the order of 10 to the 22. So this is a hopelessly large number. In fact, Tinkham gives an estimate of that, which I have not checked independently. So he says this number would be something like this. So which is needless to say, a hopeless situation. So obviously you cannot explicitly write down all those terms. What BCS did instead is to do away with this, writing this explicitly for a fixed number of electrons. So what they did was to work in within the grand canonical ensemble where the number of electrons are not fixed. Okay, but as we'll see subsequently, that the way they constructed the wave function, the fluctuations in the electron number is rather small compared to the total number of electrons. So you essentially get the average quantities right. So the BCS mean field is written this way. The difference here is that we have not attempted to choose n by 2 k points out of a total m. Instead, what they did was to include all the k points and introduce these two quantities, u of k and v of k. These are just numbers. It can be, for now we can take them to be real, but they can be made complex also. That will come, we'll see. So they are just numbers, and u squared is the probability that the state k and minus k so you don't create that pair, and bk squared is the probability that this pair is created. This pair of states is occupied. And that's the wave function. And starting with this wave function, and of course, you have to satisfy the condition that for each k, for this to be physically meaningful, this has to be 1. So what you realize is that this wave function is a very special case of that wave function, where some special set of GKs have been chosen. Okay, so what next? So what you can show starting from this wave function is that the average number of particles is something you can calculate in terms of these UKs and VKs. So that's an exercise. Let me see where we are. Let me try to do that, and then we'll go to that. So we are trying to calculate the average number of electrons, which is in the ground state that we wrote. So this average has to be calculated in the ground state that we just wrote. Okay. Right. So this will just be twice of because whenever you create a K up electron, you also create a K down electron. So this will just be twice of that. Okay, so we'll now write down the ground state wave function that we wrote. There is a sum over K involved here. This is sum over K involved. Okay, so that's what you have to evaluate. Here we have written as if U and V were in general complex numbers. Right. So, so what we'll do now is I'm just explaining how you manipulate the indices. So we'll pull the K sum outside, and we'll break these two. So this is a product of objects like this over all the K values. So this K sum will be pulled outside, and these will be written so that for each of these indices K, that K factor would be written separately, and whatever is not K will be written separately. So that's that K term that comes from here. And then there'll be a K term from here. Okay, and then you will have L not equal to K terms. From here. So we have to look at two factors differently. The K not, sorry, this is K not equal to L. So L not equal to K factors will be looked at separately, and then where this index is the same as this index will be looked at separately. Okay, so I think let us stop with this here, and I'll take it up and complete whatever I can in the next lecture. And now let us